often do, we're going to have a quick weather briefing about what's going on now in the next week or so, and Joe's going to do that. So, without further ado, I will go ahead and start talking about some waterspouts and dust devils. This is, I already talked about our website, but this is what it looks like. This is where you can see what our next ones are coming up. And there we are, me and Joe. All right, so what is a waterspout? You probably already know what that is, but just for completeness sake, here are some pictures. Basically, it's pretty simple. Waterspout is just a whirling column of air and water mist that it becomes visible coming down from a cloud or rising up towards a cloud. And we'll talk about the difference between why some form differently than others during the talk tonight. But they come in all different shapes and sizes and opaqueness or some translucent. So very wild phenomenon to see if you're at the beach or if you're on a boat, especially kind of more scary if you're on a boat because they can do some little bit of damage, but all together just kind of a really more beautiful phenomenon to see, less scary than say our typical tornadoes sometimes. So how do waterspouts form? Well, that question can't really be answered unless you specify what kind of waterspout it is. People often don't realize that there are two different types of waterspouts. They don't all come equally. So those two types are fair weather waterspouts, and that is the traditional waterspout. When we think of a waterspout, oftentimes that is what we're thinking of, versus a tornadic waterspout. So a few little facts about each one before we go into more detail on each one. So for the fair weather waterspouts, they form over the water, and they typically grow from the water to the cloud, so from low to high, and they can last anywhere from 5 to 10 minutes on average. On the other hand, we have tornadic waterspouts, and those form just like tornadoes do. The only difference is they just happen to be under or over the water. So there, the things that's going on in the clouds and in the atmosphere above the water, it doesn't know what's beneath it. So it just happens to be over water instead of land, and that's the only difference. So these form because there is rotation in the actual storm, and duration-wise, they can last much longer. They can be short, minutes. They can also last hours. And so actually, I was at work. I was doing something called storm data, which is where we kind of make a historical record of all the weather events that happen across the country. And so I was putting in a record of some of the tornadoes that we've had and waterspouts that we've had from tropical systems recently. And there was one that I did one for a tornado that happened over moving from northeast Connecticut into Worcester County during the remnants of, I believe it was Tropical Storm Fred. And for our description of that, when we did a survey of that tornado, it started as a tornado, and then we had said that it ended as a waterspout over Webster Lake or Lake Chug. I can't say the longest lake name in the country. But it was a tornado and it became a waterspout. That's just because it was over the water, and that's where it dissipated. So literally the only difference. All right, so we'll start with fair weather waterspouts, getting into a little more detail. So these will typically form along this dark flat base of a line of developing cumulus clouds that you kind of can see in this picture on the bottom left, similar to that. And so this type of waterspout is not generally associated with thunderstorms. So it can be oftentimes associated with just typical fair weather cumulus clouds sometimes. And so when we start to see the actual funnel of the waterspout, that actually means that it's near maturity. So it's been growing. It might just have been invisible to the naked eye. By the time we see it, it's about to its mature stage. And the ambient conditions that these typically form in are typically in light winds, and so that means that they are moving very little. So typically they kind of hover over the same spot over the water. So if you're like on a balcony at the beach and you see it out there, oftentimes it just kind of sits and doesn't move very much because the ambient winds are typically very light with these things. So a fair weather waterspout needs a large open area of water with surface temperatures, water surface temperatures that are warmer than the air directly above it. So this boundary layer between the water and the atmosphere is key because that needs to be unstable for a disturbance to form that would create a waterspout. So this disturbance happens when the water heats up the air just that's directly above it. So when the water heats up the air directly above it, that makes the air warmer than the surrounding atmosphere. And we know as meteorologists that warm air likes to rise. And so when the air is warmer than the surrounding atmosphere around it, it must mix upwards in order to try to reestablish stability. A lot of our weather across Earth is just the atmosphere trying to go from unstable to stable, trying to balance itself out. And that's what's happening here, and why we're getting an upward motion. That is the initial stages of these waterspouts. And so these waterspouts will form at the surface through the process I just laid out, and they will start to grow upwards from there. So with these type of waterspouts, like I said, thunderstorms don't have to be present, and large weather systems don't necessarily have to be present. They oftentimes are, but they don't have to be. Often cold fronts and squall lines are favorable for waterspout development to kick that off. So there are 5 stages to fair weather waterspout formation. They start with stage 1. It starts as a dark spot on the water. And so if you're, so kind of for these kind of things, I'm especially speaking to boaters and the mariner community, because this would be helpful if you're out on the water to be able to recognize the early stages of a waterspout, because it's something that you would want to avoid with your boat. So this would start as a dark spot on the water, but this probably wouldn't help you very much because it'd be very difficult to see from the surface. If you had, say, a drone or you're up in a helicopter, it'd be easier to see from above. But eventually, something that becomes more visually obvious is stage 2, where a spiral pattern starts to form on the water surface. And then after that, stage 3, this is the first feature that is more noticeable from the surface, and that would be a swirling column of wind-driven surface water, and this is known as a spray ring. So once you start to see the spray ring, then it's starting to grow in earnest, and the vortex will continue to grow upward, bringing water and moist air along with it, and growing eventually into a funnel that can reach far up into the cloud base. And then once that happens, like I said before, once the funnel is visible, it's already into the mature stage. So it's at maturity right then. And then the last stage is decay, and it'll eventually just fade away. All right, so that's all about the fair weather waterspouts. On the other hand, we have the tornadic waterspouts. So again, with these, rotation already exists within the storm. It doesn't have to start due to that boundary layer at the surface from the surface of the water to the air right above it. So these form in the clouds and they lower to the ground, just like a tornado does. So with that, I wanted to bring a slide that I talked about in our Severe Weather 101 talk about how tornadoes form. There's still a lot of research going on into exactly how tornadoes form. It's not a science that's finished. We're not finished learning. But this is kind of a well agreed upon method that many scientists agree is how tornadoes can form. So what happens is you have wind shear, which wind shear is just a difference in wind speed or direction as you go up higher in the atmosphere, and it can cause these horizontal tubes of air to be rotating. And these are going to be invisible to your eye. You're not going to see this, but as in image number 1 there, you get these horizontal rotating tubes. And then as it's moving across the ground, you get what's called an updraft, which is just vertically rising air. And if the updraft comes in contact with one of these rotating vortex tubes, it can lift it up and tilt it into the vertical. So then you have a storm that is spinning, but it is vertical now. And so if that rotation gets tight enough, then it can eventually drop a tornado, or in this case, a waterspout down from it. That's the basics, very basics of how tornadoes form. All right, so those are the two types. So what kind of threats come from each one? So fair weather, starting with fair weather waterspouts. Typically, these have winds less than 60 miles per hour. Most commonly, they would be about 30 to 40 miles per hour in that range. They will dissipate rapidly when they make landfall, and because of that, they rarely penetrate very far inland, and so they're not often a threat at all to inland areas. But they could still be a threat to any sailing craft or any mariners on the water that are caught, especially in a smaller boat. Even a smaller waterspout can do some significant damage to a boat. One quote that I saw when I was looking into this was, it's not the winds that are going to hurt you, it's the flying debris from your own boat. So yeah, just because you have 30 to 60 mile per hour winds, yeah, you might say that's not too bad. But if it's taking pieces of metal off your boat and flinging them in the air, that's going to be dangerous. Or if you have a sail, especially, that could be bad. So that's kind of the threats from the traditional ones. The tornadic ones, obviously, those are going to be more threatening. The winds can be anywhere from 65 miles per hour or higher in this case, and can cause significant damage and injuries. I mean, think of something like, if a tornado starts and we say have an EF1 tornado that's moving across the land, and it crosses a lake. Okay, yes, that's a waterspout, and then it moves on shore and it could do some significant damage or be dangerous to somebody. So yes, it was a waterspout, but it's still very strong. So with that, because these phenomena can cause significant damage, we want to be able to detect them, right? So how well are we equipped to detect these? So with the fair weather waterspouts, it often is almost impossible to spot them on radar, just because the rotation is not only just so weak, but it often starts very low at the surface and rises, so it's not really in the clouds. So it's really difficult to detect those. Most times when we can put out any sort of warning about those, it's because we've heard an alert from local sightings or gotten reports of a visual report of a waterspout. With the tornadic waterspouts, those certainly can be detected on our Doppler radar. And so how we do that is by looking at the velocity product, and we're looking for something that's known as a rotation couplet. And so I'm going to talk a little bit about, go back a little bit into what we've covered on our Radar 101 webinar about how we interpret this velocity product. So when you think of the radar, you most often think of what's known as reflectivity. That's the green. It goes from light rain is green to the heavier rain is yellow and orange, and the hail is red, purple. That's reflectivity. Velocity is purely red and green. That is showing the direction either to the radar or away from the radar, the direction of the winds. So what we're looking for is a couplet showing opposite directions of winds in a very small distance. In a certain alignment, that would mean rotation, because just because you have a couplet doesn't mean that means rotation. So it's determined by the movement of the rain or hail or whatever it is particles, and the green means towards the radar, the red means away from the radar. And we also have two different products within the velocity kind of product. One is the base velocity, that's just straight direction of the winds, and then the other one is the storm relative motion. This one takes into account the motion of the storm itself and makes it a little bit more visible when you have a rotation couplet, and I have an example of that here. So this is a look at the same storm, looking at the base velocity on the left and the storm relative velocity on the right. Because the storm relative velocity takes away the motion of the storm, it then unveils the rotation couplet within it. So it just makes it easier to detect. See here, you can see the difference, but it's not nearly as obvious as it is here. this is just a kind of a graphic diagram showing this. And so say this is our radar, and that you have the winds on the west side going away, the winds on the east side coming towards, and you have rotating cyclonic, anticyclonically. Or you see it in this example, you have the opposite, winds coming in on the west and leaving on the east, and so you have cyclonic rotation. But both of these are rotation. I don't think I have examples in here, but just because you have a couplet doesn't mean it's rotation. You can have couplets that are, that show convergence or divergence as well of winds. So winds coming together or diverging away from each other. Another thing to consider when we're interpreting these rotation couplets is how broad these couplets are. So oftentimes storms that are producing tornadoes contain things called mesocyclones themselves. So that's basically just a very broad rotation within a tornadic storm or a rotating storm. So say supercells often are rotating, the whole storm is rotating itself. It's called a mesocyclone. And so we have to, as meteorologists, we have to differentiate between a mesocyclone or a very broad rotation of the storm itself and a actual tornadic rotation, which is most often looked for something called gate-to-gate shear. So that's basically just 2 pixels that are right next to each other in the opposite direction, very strong. And that's when we really think, okay, there's a strong possibility there's a tornado or a waterspout there. For as an example, you may remember, I think it was 2 years ago now, that we had those 3 tornadoes on Cape Cod. One morning, like 8 to 10 a.m. or something like that. And I remember that we were watching these storms and these waterspouts all the way from off the coast of Long Island, and they trekked all the way, and their rotation stayed very strong the whole way. So they were waterspouts for miles and miles and miles, and we had a really good lead time on those tornado warnings because we were able to track those waterspouts on the radar velocity and know that they were staying strong as they headed towards the shore. And then as soon as they hit the shore of Cape Cod, they became tornadoes, purely a change in nomenclature, just because they were over land. So those would be examples of the tornadic waterspouts that are detectable by radar. So speaking of us watching those, so how does the Weather Service handle waterspouts and putting out warnings for waterspouts? So it depends on the situation. Could be a little confusing, but I'll try to explain it here. So it depends on the type of waterspout. So if it is a waterspout over the ocean, no matter what kind it is, we don't delineate fair weather versus tornadic. If we do see it rotating on radar, we'll put something out. And if it's over the ocean, we put out what's known as a special marine warning. You see here, and basically that's just the overwater version of either a severe thunderstorm warning or a tornado warning. It's kind of a way to look at it. A strong storm that would have hail or a waterspout that we would typically put out a severe or tornado for over land. If it's over the water, we'll put out a special marine warning or an SMW. Now, if it is a waterspout that moves on shore, then so I say the one I talked about on Cape Cod, we had special marine warnings out on it until it reached the shore, and then we connected it and matched it right up with a tornado warning over the land as soon as it moves ashore. Or if the waterspout is over a lake and it is a threat to life and or property, we'll keep a tornado warning on that. And our lakes are we don't have any big, we don't have the Great Lakes or anything really huge. So oftentimes we're not going to be having tornadoes that sit just over a lake and don't cause any damage in our region. So it's kind of difficult to have a situation where you just have a tornadic waterspout that stays over one of our tiny lakes. The third scenario would be a waterspout over a lake that is not a threat to property or life. But I just talked about. It's difficult for us to get here because our lakes are so small, but we would put what's known as a special weather statement, or an SPS out for that. All right, so that is all about waterspouts. So again, if you have any questions or anything that you want me to touch on more, put them in the chat or in the question box, and I'll get to those here in a minute. I'm just going to talk a little bit about dust devils. There's less slides about dust devils, but I wanted to touch on it because we got a question on it, and I have a little bit of personal experience with dust devils, which I'll get to at the end. So dust devils are very similar to waterspouts. It's a small, rapidly rotating wind, that column of wind that is made visible only because of the dust, dirt, or debris that it picks up. It also can be called a whirlwind, and it most often develops on clear, dry, and hot afternoons. They're not super common here, especially because we don't have a lot of dust around here. When I was out at our office in Spokane, Washington for 3 years, I saw a lot more dust devils because the middle of central Washington is a big desert, so there's a lot more dust. We don't get them that often around here unless you're at a baseball field or something. So these are caused by strong surface heating, and so they're smaller and they are less intense than a tornado, but they can have winds up to 60 miles per hour or more. And so they're often not they're not dangerous oftentimes, but they can do some damage to, small structures, and they could, loft debris that could hurt you. As far as their size, they're typically 10 to 300 feet in diameter, and the average height of them is about 500 to 1,000 feet, and they typically last only about a few minutes. All right, so formation of dust devils, getting into the weeds just a little bit, but they form in areas of strong surface heating, usually at the interface between different surface types. So you're talking about when you're going from asphalt to dirt, or even irrigated fields and dirt roads. Anywhere you can have that differential heating or difference in heating between different surfaces cause some sort of a boundary to kick it up. So typically they occur under clear skies and light winds, like I mentioned, and you basically need the ground, similar to how we needed the water to be warm enough, the surface of the water. Well, you need the ground to heat up enough and cause enough in what we call instability for a localized pocket of air to quickly rise through the cooler air above it. Again, like I mentioned, the atmosphere trying to stabilize itself always. So that sudden uprush of hot air is what makes the air to speed horizontally inward to the bottom of this newly forming vortex. So as this is happening, the air is rising and it's being rapidly replaced at the surface and funneling in to the center of this vortex. And so this rapidly rising pocket of air may begin to rotate, and if it does, and it continues to be stretched in the vertical direction, it'll increase in rotation and speed, and that's how we start to get the formation of a dust devil. All right, so a little extra credit. This is what I said. I have a little bit of personal experience with dust devils. When I was getting my master's degree at the University of Alabama in Huntsville, my master's thesis was on the dust devils on Mars. So actually, dust devils are extremely common on Mars, hundreds and hundreds a year, and we have a lot of evidence of them, whether it's from the earliest Viking landers back in the 70s, which didn't have any cameras, but we were able to recognize that there were dust devils happening because of the meteorological sensors on the landers, from the wind, speed, and direction, and the pressure. You could see as the wind speeds ramped up and then quickly changed direction. Also, the pressure dropped out as the center of the dust devil went over the lander. So that was the earliest signs of dust devils on Mars. And then we eventually got landers that had cameras and were able to send back images from the surface, as well as orbiters sending back images like the ones you see here. And you can see the dust devils and the shadows of them snaking along the ground. These are hundreds and hundreds of feet high. You can also see, so this is a video from the Curiosity rover, and you can see this time lapse of images showing the dust devil moving across the surface. And then you can also see this really cool image from the high resolution imaging experiment showing all these tracks from the surface of Mars. So just really kind of extra little tidbit that's not super relevant to us here, but just interesting that we're not the only planet that gets dust devils. They happen in outer space as well. So I think that is all that I've got. Yes. So I will, let's see if we can see what kind of questions we've got.
You want me to read some of the questions to you, Bryce?
That'd be great.
Okay. A little bit of an echo there, but that's okay. Landon and John first have the same question. What causes the rotation in a fair weather water spout, or what starts the rotation?
So you have to have, so basically there's got to be some sort of disturbance. It's any sort of vorticity, which is just rotation in the atmosphere. There's not one defined thing that this is what causes rotation, and this is why in this situation all the elements are the same, and maybe today there's a water spout, tomorrow there's not. What the difference is, there's just these perturbations in the atmosphere that can happen from differential heating, which I talked about with dust devils. Basically a boundary, if there's any sort of boundary between different land types with water spouts, it could be anything that causes one section of the water or the air to heat more or less than another, causes enough differential heating, and that causes enough of a perturbation in the atmosphere to just cause that rotation to just start to kick off, and then it kind of feeds off of itself. So there's no real like one thing, this is what always causes the rotation, but those perturbations in the atmosphere that are sometimes kind of unpredictable are what most often causes that.
All right. And just a question from Sebastian. So the waterspouts we had off the southern New England coastline with the remnants of Ida, were those considered tornadic waterspouts?
With Ida, I believe that they would. I don't remember those specifically.
Yeah, I would say yes. It's a tropical remnant system, so yeah, those would be formed like more the way you showed that the tornadic ones form.
Yes, because obviously that those spawn from a big weather system. Like I said, with the traditional ones, they're often not associated with a big system. They just happen on their own, and so the fact that those happen with tropical remnants, it would definitely make me think tornadic.
Okay. Let's see. And he just had another comment on the velocity data. He's pretty sure he remembers seeing something where strong or even severe storms have divergence aloft that can be detected with the higher velocity tilts. Yeah, that is correct. And that's actually one of the things you look for a severe storm, is that strong divergence aloft or spreading out like Bryce was talking about. Yep. So bingo. Okay, we got one from our friend Nick, age 12. Okay. Do waterspouts have their own scale, like the EF scale for tornadoes?
Oh, good question. Actually, that is great. They do not. There's no scale to measure the strength of a waterspout. Only tornadoes have such a scale.
So Bryce, and remind me, because I did storm data years ago that you're doing now. I think we put a wind speed estimate though for them, or if we know it.
Yes. We will typically estimate the wind speed, but we don't have any sort of label on it, like, oh, this is a EF1 waterspout.
Right. Okay. Well, maybe someday, there's something Nick can work on when he goes to school for meteorology. That sounds like a good graduate school research project. All right. Okay. From Sebastian, let's go to your Mars research, Bryce. Would dust devils be stronger on Mars, or would they be about the same intensity as the ones we experience on Earth? That's a good question.
That's a really good question. So, it's not a straightforward answer. So they are very strong and often much stronger than the ones here on Earth if we're talking straight wind speeds. But the caveat is that doesn't mean that they're more impactful, because the atmosphere on Mars is so thin that even I'm pulling these numbers out the top of my head, but 100-mile-per-hour wind may blow a flag a little bit. Because the atmosphere is so thin that even these strong winds that would cause a lot of damage on Earth would not cause that damage on Mars. So if one kind of example of this that I noticed if you ever seen the movie The Martian, with Matt Damon. The whole premise of the movie kicks off because there's a dust storm on Mars and their spaceship gets knocked over. So they're trying to leave and the spaceship gets knocked over because of those strong winds. So actually, if the movie was scientifically accurate, the movie never would have happened because the winds could never have knocked over the spaceship because the atmosphere is so thin. Even 300-mile-per-hour winds wouldn't have knocked it over. So, yeah, the answer is yes, but also no.
Okay, that's a good answer. And let's see, another one from Sebastian. Are the mechanisms that we discussed during this webinar similar to what would produce a non-supercell tornado? So you want to take a stab at that, Bryce, or I can help too?
I don't know. I mean, I really am not sure about that one. Do you have any idea?
Okay, I would say, yeah, there are. I mean, it's all similar. You have to have the rotation. So I think from the research we've done, a lot of the tornadoes we have are not the mesocyclone produced ones. June 1st, 2011 aside, we'll use that as our caveat. That definitely was. A lot of them are actually spin up from the ground, much like you showed, Bryce, during the waterspouts, the almost the fair weather type waterspouts that the rotation starts near the ground and works its way up into the cloud. We've actually found that a lot of the tornadoes here form that way as well. They form from the ground up. So that's why a lot of times we'll see damage on the side of a hill or somewhere where the air can be forced up. So, but the mechanism is pretty much the same. You have to have the rotation. It has to be tight. We call it all tight and bright on the radar. We've used that term before. So yeah, Sebastian, I would say take what Bryce showed you about the fair weather waterspout, and it's just obviously a lot stronger, on much stronger rotation than what we're seeing there. But that process is actually pretty similar. So good observation. And if Sebastian, if I remember, you were the one who suggested this topic, so thank you for that. Bryce was all over this. It was great. And let's see, we have one more right now from John. Bryce, is the rotation in waterspouts and dust devils always cyclonic? Good question.
Good question, and I don't know for sure, but I would guess no because it's similar with tornadoes. Their tornadoes aren't always cyclonic. They typically are, but we do have anticyclonic tornadoes, so I would assume that we could also have anticyclonic waterspouts. Do you have a
Yeah, yeah,
different?
yeah. The most of them are cyclonic, meaning counterclockwise, but occasionally you can have an anticyclonic or clockwise rotation. It's pretty rare, and Bryce, I don't think I've ever seen one in all
I,
my years of watching radar, but
yeah, I have never.
they do happen. They've been documented out in the plains, obviously, where they have more. So, all right. Well, those are all the questions for now. Um, do we want to move on to our briefing, Bryce? I can.
Let's do it.
Let's pause the recording so we don't have to keep it going. Bryce, if you want to share the screen with me, I can go ahead and just show a few things. And again, if you have any questions you might have thought of while we're going through the weather briefing, throw them in the chat, or if you have any questions on the briefing,